Let's just dive right into this. Welcome to The Explainer, where we unpack complex source materials so you can see exactly how the world works, slide by slide. Today, we've got a brilliant engineering detective story. We're looking at how a massive source of manufacturing waste in the digital camera industry is being completely defeated. It's all about perfection, perception, and honestly, a whole lot of very expensive silicon. Seriously, have you ever actually wondered why your phone's camera module might only cost a manufacturer a couple of bucks, but it captures these stunning, high-res photos that totally rival professional gear from just a decade ago? To figure out how we get such affordable technology, we have to look at the microscopic battle happening inside every single image sensor on the assembly line. So here's our roadmap for the explainer today. 1. The myth of perfect pixels. 2. Unmasking PRNU defects. 3. The standard testing flaw. 4. A smarter system level test. And finally, 5. Saving sensors and lowering costs. All right, Section 1. The myth of perfect pixels and imperfect manufacturing. Look, every single digital camera sensor out there, specifically the CMOS sensors packed into our modern electronics, is made up of millions of microscopic light-gathering buckets. And here's the harsh reality. Perfect pixels are literally impossible to make. Perfect uniformity? It's a total illusion. As sensors shrink down to fit inside our incredibly thin smartphones, and as the pixels themselves get smaller, we're talking less than 3 micrometers across, trying to deliver a flawless image from millions of unique microscopic components becomes just this absolutely unbelievable engineering challenge. You'll notice engineers actually categorize these microscopic flaws into 3 main types. First, you've got your hot pixels, which are essentially stuck on max brightness. Then you have cold pixels, which are totally dead, just stuck low. Now, both of those are relatively easy for camera software to spot and patch up just by looking at the neighboring pixels. But then there is our main villain for today, PRNU. And this one is caused by incredibly slight physical variations in the design of the pixel itself. Which brings us to Section 2, unmasking PRNU defects. What exactly is PRNU? Well, PRNU stands for photoresponse non-uniformity. Simply put, it means that if you shine the exact same amount of light on 2 adjacent pixels, they're going to output slightly different brightness levels. And worse, it's a signal-dependent defect. Basically, it acts like a multiplier. So the brighter the light hitting the sensor, the more obvious that annoying PRNU difference actually becomes. And this variation happens right at the physical, microscopic level. If we look at a single pixel's circuitry, you can see the variation happens right at the photodiode. Maybe its surface area is just slightly off, or its capacitance varies a tiny bit because of manufacturing doping quirks. It also happens right at the source-follower transistor, the part that amplifies the signal. Honestly, even a tiny 1 to 5% variation in how these parts are fabricated can completely alter the gain of that specific pixel. Let's move to Section 3, the standard testing flaw. This was a major blind spot. See, traditionally, these sensors were tested in a total vacuum on the factory line. Engineers would shine a perfectly uniform light right on the raw sensor, calculate the PRNU variation, and then apply this incredibly strict pass or fail grading system. But this completely ignored the context of the actual photo. It ignored how the camera software, the image processing, the JPEG compression, the color correction, might naturally hide or just process out those microscopic flaws by the time the picture actually shows up on your screen. The real kicker here is when you compare these distributions. The old testing standard used an RMS, or root mean square average, to measure PRNU across a block of pixels. So standard testing would look at these 2 blocks and treat them exactly the same, because statistically their average variation is identical. But just look at them. The block on the left has a smooth Gaussian variation. The block on the right has 2 sharp, intense defective pixels. That's impulse noise. Our human eyes clearly lock onto that sharp contrast on the right way more intensely. Yet, the old standard metrics couldn't really distinguish between what a computer detects and what a human actually notices. So the testing flaws were really stacking up, because the old methods sometimes averaged out extreme outliers, or on the flip side, punished sensors for tiny variations that we would literally never notice. The whole process was highly inefficient. It totally failed to account for human visual sensitivity to contrast. And get this. To even find the PRNU, factory testers would average together 16 frames of a photo to strip away all the natural camera noise just to isolate it. But in the real world, you don't take 16 photos and average them out. You take 1 photo, complete with random noise that often just naturally covers up the PRNU anyway. The end result? perfectly usable sensors were being tossed straight into the trash. Enter Section 4, a smarter system-level test, taking a smarter approach. The massive paradigm shift here was moving from that old rigid way to a much more contextual new way. Instead of asking, hey, is this raw silicon sensor absolutely perfect? The new method asks, is the final image degradation acceptable to a human eye once all the image processing and JPEG compression are applied? It is a totally different way of looking at quality control. As you can see in this flowchart, engineers mapped out a new blueprint. They realized they could still use the fast, standard factory measurements for raw PRNU, but then they'd feed those measurements through advanced simulations. These simulations actually mimic real-world camera usage to correlate the raw data against specific application error rates. Let's see how this plays out in the full system pipeline. This noise transfer diagram maps out what actually happens inside your camera. When you snap a pic, you don't just capture PRNU. You get photon shot noise from the light itself. You get read noise from the electronics. You get dark current noise. By factoring in all of these other noises, engineers discovered a mathematical knee point. If the PRNU noise is lower than the random background noise of the camera, the human eye literally cannot see it. That random noise acts like an invisibility cloak for the PRNU defects. So this elegant solution breaks down into 4 clear steps. First, determine the target application. A high-speed industrial camera obviously has different tolerances than your standard consumer low-light camera. Second, run probability models that actually include how much JPEG compression will blur the final image. Third, establish PRNU thresholds based on actual human vision, not just raw math. And finally, step 4, classify the sensor. Because of this process, a sensor that fails a super strict test for a $1,000 professional camera might be totally fine and reassigned to a budget $50 camera instead of just being destroyed. Which takes us to our final section, Section 5, saving sensors and lowering costs. 4.5%. In the massive global scale of semiconductor manufacturing, up to 4.5% of CMOS image sensors were previously just lost. That is a massive yield drop, and it was happening simply due to excessive, misunderstood PRNU. Millions of chips discarded because they were being judged on this impossible, completely out-of-context standard of perfection. But by changing how we test and actually embracing this concept of acceptable system-level degradation, manufacturers are preventing perfectly good sensors from ending up in a landfill. And here's why this matters directly to you. This highly technical math, understanding human visual thresholds and JPEG masking, is exactly why your next smartphone camera module might cost $50 to manufacture instead of $150. When manufacturing yields go up, your consumer costs come right down. Which leaves us with a pretty fascinating final thought from this explainer. Context really is everything. It really makes you wonder about the power of perspective in engineering, doesn't it? I mean, if a simple shift in testing context can rescue millions of discarded microchips and lower our tech bills, what other supposedly flawed innovations out there are we throwing away right now simply because we lack the right perspective to see their hidden value? Thanks for joining me on this deep dive. I hope it sparked your curiosity, and I'll catch you next time.